Part 3, slant asymptotes. We've talked about vertical asymptotes and we've talked about horizontal asymptotes, but sometimes a rational function will have a slant asymptote. Here's an example right here. That dashed line is a slant asymptote, and as x is getting bigger and bigger and bigger, or smaller and smaller and smaller, so as x is approaching infinity or negative infinity, the graph is getting closer to that asymptote. So let's talk about how to find slant asymptotes. We know a rational function has a slant asymptote if the degree of the numerator is exactly 1 more than the degree of the denominator. Y equals L of x is what we call the slant asymptote, where L of x is the quotient obtained by dividing P of x by Q of x. And when we do that division, we can then ignore the remainder, because the asymptote applies when x is getting really, really big or really, really small, and so the remainder would be negligible. If a rational function has a horizontal asymptote, it does not have a slant asymptote. So it can have a horizontal asymptote, a slant asymptote, or neither. And slant asymptotes are sometimes referred to as oblique asymptotes. Either word works just fine. Let's determine if these functions have a horizontal asymptote, a slant asymptote, or neither. And if there is a horizontal or slant asymptote, we'll find the equation. Part A, f of x equals 3x plus 2 over 7x squared minus 5x plus 3. The degree of the numerator is 1. The degree of the denominator is 2. So when the numerator has a smaller degree than the denominator, we have a horizontal asymptote at y equals 0. Part B, g of x equals 3x cubed minus x squared plus 4x minus 1 over x squared minus 2x plus 3. The degree of the numerator is 3. The degree of the denominator is 2. So the degree of the numerator is 1 more than the degree of the denominator, so there is a slant asymptote. And to find that asymptote, we need to divide. So we'll do long division for this one. We have x squared minus 2x plus 3 into 3x cubed minus x squared plus 4x minus 1. Do the division. X squared goes into 3x cubed. 3x times x squared is 3x cubed. 3x times negative 2x is negative 6x squared. And 3x times 3 is 9x. Subtract, and we get 5x squared minus 5x minus 1. And then x squared goes into 5x squared 5 times. Multiply, we have 5x squared minus 10x plus 15. Subtract, and we get 5x minus 16. Now 5x minus 16 has a smaller degree than what we were dividing by, so that part's our remainder. And we said we can ignore the remainder when finding the slant asymptote. So our asymptote is the line y equals 3x plus 5. Part C, h of x equals 5x to the 5th minus 7x cubed plus 2x minus 3 divided by x cubed minus 5x squared plus 7. The degree of the numerator is 5. The degree of the denominator is 3. So the numerator has a bigger degree, but remember there's only a slant asymptote if the numerator is exactly 1 more. The degree of the numerator is exactly 1 more than the denominator. Here the degree of the numerator is 2 more than the degree of the denominator, so there is not a slant asymptote or a horizontal asymptote here. However, if we were to divide the leading terms, 5x to the 5th divided by x cubed, we would get 5x squared. That is not an asymptote because it is not a line, and asymptotes are lines. But as x gets really big, so as x approaches infinity or negative infinity, the graph of h of x will start to resemble the graph of 5x squared. Let's practice graphing a rational function with a slant asymptote. First, we'll find the domain of r of x equals x squared over x minus 2. So x cannot be 2 because that would make us divide by 0, and we can't do that. In interval notation, we have negative infinity to 2, union 2 to infinity. Holes, there are holes in the graph. If there's a common factor in the numerator and denominator, we cancel out. In this case, there are no common factors to cancel, so there are no holes. Finding the x and y intercepts. The x-intercept is where the numerator is 0, and the y-intercept is when x is 0. Either way, our only intercept is the point 0, 0. The vertical asymptote are where the denominator is 0, so that would be x equals 2. The numerator has a degree 1 higher than the denominator, so there is a slant asymptote, and we can find that slant asymptote. We can actually use synthetic division for this one, or you could use long division. 2 times 1 is 2, 2 times 2 is 4. We ignore the remainder, so our horizontal or slant asymptote is a slant asymptote, and we get y equals x plus 2. Let's graph this function. Our intercept is 0, 0. Our vertical asymptote is the line x equals 2. Our slant asymptote is the line y equals x plus 2. So we have a y-intercept of 2 and a slope of 1. Okay, so there's my two asymptotes. Now I need to decide how to graph this. I only have one point. It is 0, 0. I do know that the graph is going to touch and turn around at 0, 0 because this is an even multiplicity on that factor. So the graph will likely look something like this and then getting closer to those asymptotes. And up here on the right side, if we plug in another point, let's plug in 3. If I plug in 3, I get 3 squared over 1, which is 9. So I have a point at 3, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And my graph is going to get closer to these asymptotes, so something like that. General steps for graphing rational functions. Part 1, determine the domain and the coordinates of holes. Find and plot the x and y intercepts. Determine and plot the vertical asymptotes. Then find the horizontal or slant asymptote. Plot additional points as necessary to complete the graph and determine if the graph crosses the horizontal asymptote. Go ahead and find as many points as you want to. If you're not comfortable with where your graph is or the shape of your graph, plot more points. And you could also determine whether the graph crosses a slant asymptote. So our graph will never cross a vertical asymptote, but could cross the horizontal or slant asymptote. So let's try this function. F of x equals x cubed minus 3x squared minus 4x plus 12 divided by x squared minus x minus 2. If I factor this, I should get x minus 2 times x plus 2 times x minus 3 divided by x minus 2 times x plus 1. So my domain x cannot be 2 or negative 1. Then I can cancel out my like factors, and I have x plus 2 times x minus 3 over x plus 1. I'm going to use that function now to find everything else. So to find the holes, I crossed off x minus 2, so that's where x is 2. My hole will occur when x is 2. Plug in x is 2 into this function. I get 2 plus 2 times 2 minus 3 over 2 plus 1, which gives me 4 times negative 1 over 3, or negative 4/3. So my hole is the point 2, negative 4/3. Find the x and y intercepts. So remember, simplified, this was x plus 2 times x minus 3 over x plus 1. The x-intercepts are where the numerator is 0, so negative 2 and 3. And the y-intercept is when x is 0. So if all the x's are 0, I have 2 times negative 3 over 1, which is negative 6. The vertical asymptote would be x equals negative 1. That's where the denominator equals 0. And this will have a slant asymptote because the numerator has a degree 1 higher than the denominator. If I multiply through in that numerator, I do get x squared minus x minus 6 over x plus 1. And I can do synthetic division because I'm dividing by x minus a negative 1. So to find my slant asymptote, I do the synthetic division. And I can ignore the remainder. And my slant asymptote is y equals 1x minus 2. Okay, let's graph this function. We have an x-intercept at negative 2 and an x-intercept at 3. And we are going to cross through the x-axis at both of those. Both of our factors in the numerator have odd multiplicities. We have a y-intercept at 0, negative 6. A vertical asymptote at x equals negative 1. And a slant asymptote at y equals x minus 2. Okay, so we have a bunch of points. What is this going to look like now? We already said we're going to cross through the x-axis at both of those x-intercepts. So these 2 points, there's no vertical asymptote between them, so they will connect and then start getting closer to those asymptotes. My hole is the point 2, negative 4/3. I'm going down on the right side of that vertical asymptote, so I need to be going up on the left side because this vector where we found the vertical asymptote has an odd multiplicity. And then we cross through the x-axis at that intercept. And there is our graph.